In this video, we'll do a first example of a second order RLC series circuit here. In this case, there's nothing else going on in the circuit, it's just the RLC in series, and in fact they even gave you the initial values. The initial current through the inductor is 4 amps, and the initial voltage across the capacitor is negative 4 volts. In most normal problems, you have to figure that out for yourself based on what's going on in the circuit. Now we know that for RLC series circuit, the standard differential equation is x double prime plus r over l x prime plus 1 over LC x equals some constant here. And it depends on what you're looking for. If I'm looking for the actual current, which is what I have in this problem, then we know it's going to be I double prime plus R over L I prime plus 1 over LC I equals 0. Now we're going to go ahead and take this and solve it. So we plug in our specific numbers here. The R is 6, the L is 1, so we're going to have 6 I prime. And then L times C, L is 1, C is 0.04. So we do L times C, we get 1 times 0.04 is 0.04. And then if we do 1 over that, we get 25. So we have plus 25 here, I equals 0. We go ahead and write our characteristic equation. S squared plus 6x plus 25 equals 0. This doesn't factor nicely, so we'll use our quadratic formula. B squared minus 4AC over 2A. And we're going to have negative 3 plus or minus. Let's see, 36 minus 100 is negative 64. It's going to be 8I divided by 2 is going to be 4I. So that means our standard homogeneous solution is I of t is k1 e to the negative 3t, cosine of 4t plus k2 e to the negative 3t sine of 4t. And then in general, for the non-homogeneous solution, you have to say plus some sort of constant here. However, since we are doing the current through an RLC series circuit, the current at infinity is going to go to 0 because it's going to be an open circuit, and that number you add there is always going to be the value at infinity. So there's no number there. Also, it's the homogeneous version because it's nothing else is going on here, and we're looking for the default current. So now we need to find out what we have. Well, we know that if you plug in 0 for the current, well, the current here, I of t, is going to be the same as the current through the inductor. So it's going to be 4 amps. And if you plug in 0 to that formula, k1, e to 0 is 1, cosine 0 is 1, then plus k2, e to the 0 is 1, but sine of 0 is 0. So that tells you that k1 is 4. Now, to find our k2, it's going to be a little bit tricky here. And so we got to think about what the best way to approach this. Well, we know that the voltage at the source, that's 0 volts. At time t equals 0 plus, we know that the current is 4 amps, which means we're going to have a 16 volt drop across the resistor. We know the voltage across the capacitor is a negative 4 volts. And so then by Kirchhoff's voltage law, if we kind of go around the loop here, we have a gain of 0, a loss of 16, we'd be at negative 16, a loss of negative 4, or a gain of 4 is at negative 12, so we need another gain here. It would be a negative 12 volts across the inductor. And now that we know the voltage across the inductor at 0, we know that for inductors, we know that the voltage is L times the derivative of the current. So if I go ahead and take the derivative here, I prime of t, Well, I know what K1 is, 4, so I'll include that. And then we're doing product rule here, negative 3 e to the negative 3t cosine 4t plus e to the negative 3t times negative 4 sine of 4t. And then plus K2, product rule again, negative 3 e to the negative 3t sine 4t plus e to the negative 3t for cosine 4t. So now we have our derivative, and we know if you plug in 0 and multiply times L, you get the voltage at 0. Well, the voltage at 0, as we just worked out, is negative 12. And if we do our L, IL is 1 here, times I prime of 0. And we know what I prime of 0 is. Let's see here. Everything, the cosine is going to stay, everything sine is going to go away. So we have 4 times negative 3 plus 0 plus K2 times 0 plus 4. So we're going to have negative 12 equals negative 12 plus 4K2. That means my K2 is 0 in this case. So after all that work, my final answer then is I of t is equal to 4 e to the negative 3t cosine of 4t, and then the K2 part goes away, and this is in amps. So this was about as easy as it's going to get. Normally, we're going to have to find our initial conditions ourselves, but we are going to always have to take derivatives and compare things, and it's a big, long process, and you really want to do many examples until you understand all the steps of the process and you can recreate them on your own.